Good morning. Today I'm going to discuss the first part of Module 5 of the course CE206 Fluid Mechanics 2 for second year civil engineering students of Kerala Technological University. Module 5 is on gradually varied flow, and in this lecture I'll be discussing about the basics of gradually varied flow. So let's start with the definition of gradually varied flow. Gradually varied flow is a steady, which means it does not vary with time, non-uniform flow, which means that the depth of the flow varies with distance. That is what is meant by non-uniform. Steady means the depth of the flow does not change with time. However, the depth of the flow changes with distance. So a steady, non-uniform flow in a prismatic channel with gradual changes in its water surface elevation is called as gradually varied flow, or in short we will call it as GVF. So I'll describe GVF to you using a figure. So this is the channel bottom. The flow is taking place and I've also shown the flow direction. Now suppose there is an obstruction in the path of the flow. Now if the flow continues to flow at the same level, if the flow continues at the same level, it will not be able to overcome the obstruction. So slowly the flow depth starts to increase, so that ultimately by the time it reaches the obstruction, it will be able to pass the obstruction. So this is how the depth is going to vary as it reaches close to the obstruction. It flows over the obstruction, and after it flows over the obstruction, a hydraulic jump is formed. Hydraulic jump has already been discussed as part of module 4, so I hope you all will be remembering. So this is a flow process where water is flowing, it reaches an obstruction, so it has to slightly increase its depth in order to overcome the obstruction. It flows over the obstruction and a hydraulic jump is formed. Now I'll explain gradually varied flow to you using this figure. I'm drawing a straight vertical line here. Now to the left of this vertical line, I have flow depth that does not change with distance. And you can see flow depth is constant. It does not change as you move ahead along the flow. This part of the flow is known as uniform flow. The remaining portion, you can see that the flow depth keeps on varying along the flow, along the length of the flow, and so the remaining portion becomes non-uniform flow. Now there are two portions to this non-uniform flow. If you look at this portion where the hydraulic jump is getting formed, you can see that within a very short distance, that is within a very short length of the channel, the depth of flow is varying abruptly. That is, from a small depth here to a very high depth over here. All this is happening over a very small length of the channel, and so this portion of the non-uniform flow is known as rapidly varied flow or RVF. So the remaining, if you can see, the remaining portion of the flow from here till here, you can see that the flow depth is not constant. It's going to keep on varying. However, the variation in the flow depth is slow and it's not abrupt, and over a large length the increase in depth of flow is very small. And so this portion where the flow depth is increasing gradually is known as gradually varied flow or GVF. So your uniform flow was discussed as part of module 3, and rapidly varied flow was discussed as part of module 4. So in module 5 we will be concentrating on this part, which is gradually varied flow. Gradually varied flow, if you want to quantify gradually varied flow from one point in a stream to another point, for the depth to rise by 1 meter, maybe the stream has to travel kilometers, maybe 10 kilometers or 15 kilometers distance, so that its level changes by 1 meter. So you can see that it is continuously, it is varying, the depth will continuously vary. However, the length taken for the depth to vary is very large. And so the variation in the depth is very, very gradual, and that is why it's called as gradually varied flow. Now we have to analyze gradually varied flow in order to get a mathematical expression for the same. So before we analyze gradually varied flow, we'll look at the assumptions of gradually varied flow. The first assumption is that the pressure distribution at any section is assumed to be hydrostatic. That is necessary for us to analyze. The second assumption, please look at it closely. The velocity of flow at a given depth for a gradually varied flow is assumed to be given by the corresponding uniform flow equation, such as the Manning's equation or the Chezy's equation, with the condition that the slope term to be used in the equation is the energy line slope SF instead of the bed slope S0. So you might not be able to decipher this just by reading the statement, so I'll explain it to you using the equation. This is the figure that gives you the three different slopes of an open channel flow. S0 is the slope associated with the channel bottom, SW is the slope associated with the water surface, and SF is the slope associated with the total energy line. So if it was uniform flow, SF is equal to S0 is equal to SW, and the equation would have been Chezy's equation, V equal to C root R S0, or Manning's equation, V equal to 1 by N R raised to 2 by 3 S0 raised to 1 by 2. Now I hope you already remember the terms. V stands for velocity, C is Chezy's constant, capital N is Manning's constant, capital R stands for hydraulic mean depth, which is area divided by wetted perimeter, and here S0 stands for the slope of the channel bottom. This is the equation for uniform flow when the depth of flow does not vary with distance. Now you can apply the same equation for gradually varied flow as well. However, with a slight change. For gradually varied flow, we will use velocity is equal to C root of RSF. So instead of S0, which was the uniform flow equation, we will use SF, which is the energy line slope of the total energy line. If we are using Manning's equation, V is equal to 1 by N R raised to 2 by 3 SF raised to 1 by 2. So you can see the difference. In uniform flow, for slope, we used to use the bottom slope, channel bottom slope, whereas for gradually varied flow, we will be using the energy line slope. So that is what is written in the second assumption. The velocity of flow at a given depth is assumed to be given by the corresponding uniform flow equation, like a Manning's equation or Chezy's equation, with the condition that the slope term to be used in the equation is the energy line slope SF instead of bed slope S0. So if you're analyzing gradually varied flow, you can use the same equations as uniform flow, but instead of using channel bottom slope, you will have to use slope of the energy line. So moving ahead, this is I'll again come to the figure in order to explain the analysis of gradually varied flow to you. This is the datum. You have the channel bottom with channel bottom slope S0. There is the water surface, and there is the total energy line with a slope of SF. Now I'm going to take the depth. Z1 is the distance from the datum to the channel bottom. Y1 is the distance from the channel bottom to the water surface, and V1 squared by 2G is the distance from the water surface to the total energy line. So analysis like this we have done in the lecture in module 4 when we were discussing about specific energy also. So I don't think this would be something new to you. Now what I'm going to do is, at a distance, horizontal distance dx, I'm going to take another section. I am going to denote the distances at this section. The distance between the datum and the channel bottom is Z2. the depth of flow is y2, and the distance between the water surface and the total energy line is V2 squared by 2g. So I have the total energy of section 1 and total energy of section 2. Now if I want to find out the difference between the energies at sections 1 and 2, I'm going to draw a horizontal line here, and this is the difference of energies between sections 1 and 2. Now this particular value, I know that the slope of this line is SF and this distance is dx. So naturally this vertical distance is going to be SF into dx. If you want, you can simply work out tan theta. Tan theta is equal to dx divided by this vertical distance. But what is tan theta? Tan theta is SF. So this vertical distance would be SF into dx. However, I have written it as minus SF into dx. I just told you that the vertical distance is SF into dx, so I have written it as minus SF into dx. How did the negative sign come? The negative sign is given because the slope decreases with an increase in distance. And that is why, in order to denote that, a negative sign has been given. So now I am going to compare these two values. From the figure, I can simply write Z1 plus Y1 plus V1 squared by 2G is equal to Z2 plus Y2 plus V2 squared by 2G minus SF into dx. Now I'll bring Z1, Z2 and Y2 and V2 terms to the left hand side. So I will get Z1 minus Z2 plus Y1 minus Y2 plus V1 squared by 2G minus V2 squared by 2G is equal to minus SF into dx. Now Z1 minus Z2, I am going to denote it as dz. Y1 minus Y2, I am going to denote it as dy. And V1 squared by 2G minus V2 squared by 2G, I am going to denote it as d of V squared by 2G. It is equal to minus SF into dx. Now I am going to divide throughout with dx. I will get dz by dx plus dy by dx plus d by dx of v squared by 2g is equal to minus sf. It's not over. We're going to continue analyzing. This derivation, just like the non-dimensional equation for a hydraulic jump, I had told you that it's a lengthy derivation. You have to do this derivation alongside with me. It applies to any derivation in fluid mechanics. Do not simply watch the derivation being done. If you want to understand it and if you want to answer it for your exam, it would be better if you would do the derivation alongside the video as the video is progressing. You can pause the video if you have a doubt. Do the derivation alongside me so that you will be able to understand what exactly is being derived and how we arrived at this particular equation. So now we're going to move forward. The figure is kept as it is because it would be helpful. Now this was where we ended. Dz by dx plus dy by dx plus d by dx of v squared by 2g is equal to minus sf. Now d by dx of v squared by 2g, what I'm going to do is v squared by 2g from the lecture on specific energy, we know that v squared by 2g is small q squared by 2g y squared. So I'm going to replace v squared by 2g. Oh, before that, dz by dx is given by minus s naught. Now I'll tell you why. Dz by dx is z1 minus z2 divided by dx. So z1 minus z2 divided by dx is equal to this slope S naught, the channel bottom slope S naught. So the negative sign has been given over here so that it can compensate for the fact that the slope is decreasing with increasing in distance. Just like we gave minus sign for SF, we are going to give minus sign for S naught also, because the slope is decreasing as the length is increasing. So minus S naught plus dy by dx plus d by dx of v squared by 2g is equal to minus sf. Now like I told you earlier, v squared by 2g, I'm going to replace it with q squared by 2g y squared. S naught I have taken it to one side. So dy by dx plus d by dx of q squared divided by 2g y squared is equal to S naught minus sf. So I'm going to differentiate this term here because it's not in its simplest form. Q squared and 2g are constants. I can take it outside. D by dx of 1 by y squared. 1 by y squared, when you differentiate with respect to x, you're going to get it as minus 2 divided by y cube into dy by dx. So substituting, I will get dy by dx minus 2q squared by 2g y cube dy by dx is equal to s naught minus sf. 2 and 2 will get cancelled off. Dy by dx can be taken common outside, and I will get dy by dx is equal to, dy by dx into 1 minus q squared by 2gy, the q squared divided by gy cube is equal to s naught minus sf. Or I will get dy by dx is equal to s naught minus sf divided by 1 minus q squared by gy cube. So you should understand what is dy by dx over here. Dy by dx is the rate of change of flow depth along with distance. So the change in the water surface elevation with distance is dy by dx, and it is given by s naught sf divided by 1 minus q squared by gy cube. Now it's not yet the final form. We can further improve or further simplify this expression. I have kept the figure as it is. So dy by dx is s naught minus sf divided by 1 minus q squared by gy cube. Now q squared by gy cube, small q is capital Q by b, so capital Q squared by b squared. Y cube, I split it into y squared into y. So q squared divided by b squared, y squared would become v squared. Velocity, q divided by area is velocity, so velocity squared divided by gy, which is nothing but v by root gy the whole squared. V by root gy is the fluid number at the depth y, and so I will get q squared divided by gy cube is equal to fluid number the whole squared, which I can substitute it back over here. So dy by dx would be s naught minus sf divided by 1 minus fr squared. This is the final form of this of the gradually varied flow analysis, and this is known as the dynamic equation for a gradually varied flow. This is the dynamic equation for a gradually varied flow. This is what we have derived till now. This is a lengthy derivation again. A very common question used to be asked for the university exam. Derive the dynamic equation for a gradually varied flow. It's a very simple derivation, even though it is lengthy. So if you should practice it more than once. You have to write it down and learn it more than once so that it stays in your head. The formula also can be directly applied in numerical problems. So the dynamic equation for the gradually varied flow, we just derived it as dy by dx is equal to s naught minus sf divided by 1 minus fr squared. Now before we finally arrived at this expression, we had certain earlier expressions, which was dy by dx is equal to s naught minus sf divided by 1 minus q squared by gy cube, or dy by dx is equal to s naught minus sf divided by 1 minus v squared by gy. V squared by gy is the same as q squared by gy cube, or it's the same as fr squared. So I've simply substituted fr squared in different ways. Now why I've done this is because all these three forms can be used when we are solving numerical problems. In numerical problems, depending on the data that is given to us, we can use the equation form number 1, number 2, or number 3. There are 3 different forms for dynamic equation of GVF, all exactly the same equation. However, I've substituted in different ways because each numerical problem will be giving you different data, and so you need to know which equation can be easily used to get an answer. You can use any equation to get the answer, but certain equations can directly or easily give you the answers on substituting. And so you need to know all 3 forms. Let's move ahead to numerical problems. First question. Find the rate of change of depth of water, that is dy by dx, in a rectangular channel of 10 meter width and 1.5 meter depth when the water is flowing with a velocity of 1 meter per second. The flow of water through the channel of bed slope 1 in 4000 is regulated in such a way that the energy line slope is 0.00004. So first, like any other numerical problem in fluid mechanics, we start with writing down the given data. So given that the width is 10 meter, the depth is 1.5 meter, velocity of flow is 1 meter per second, bed slope is given as 1 in 4000, so 1 divided by 4000 is 0.00025, that is the bed slope S0. Energy line slope is SF, SF is given by 0.00004. So these are the data that are given to us. Now these can be directly used in order to solve for dy by dx, because the question is asking us find the rate of change of depth of water. That is nothing but dy by dx. So dy by dx, I am going to use the formula dy by dx is equal to S naught minus SF divided by 1 minus V squared by Gy. I am going to use this formula because I already know V and Y. So using this formula, I will be able to get the answers very quickly. So S naught is given, SF is given, velocity and depth is given. Everything can be substituted as shown, and you will end up getting dy by dx is equal to 2.253 into 10 raised to minus 4. Always work out problems by pausing the video, working out the problem and then checking the solution. Do not go through the solution and then try to do the problem. This will actually hinder your thinking process, because you will start thinking like the person who is lecturing the video. Everybody has thoughts of their own. You can use there are 3 different forms of dynamic equation. You can use your own brain, and you can use any one of those 3 forms to arrive at the answer. Do not let your brain be clouded by what someone else is telling, because you will also end up with the same answer in your own way of thinking using this similar equation. Okay, so always first do the problem and then only compare the answers with the answer that has been done by me. So we'll go to the second problem. Find the slope of free water surface in a rectangular channel of width 20 meter having depth of flow 5 meter. The discharge through the channel is 50 meter cube per second. The bed slope of the channel is given by 1 in 4000. Take Chassis C equal to 60. Now they've given Chassis constant, so there must be something here. We'll just go through what are the data that are given to us. Given that B is equal to 20 meter, depth of flow is 5 meter, discharge is 50 meter cube per second. Now capital Q is not used in dynamic equation, so I'm going to convert it into small q because I know the width. Small q is capital Q by B, so 50 divided by 20, I'll get 2.5 meters squared per second. Then bed slope is given 1 in 4000, 0.00025, and Chassis C is given as 60. Now one major problem is that energy line slope is missing in this problem. Now how do you solve for energy line slope, or how do you find out energy line slope? Because dy by dx numerator is S naught minus SF. SF is not given, which means that you would have to find out SF. So you see Chassis C is being given to you, so something strikes you. In the beginning of this presentation I told you that in non-gradually varied flow you can use the same equation as your uniform flow, except that you have to replace bed slope S naught with energy line slope SF. So Chassis C is given, and I know that V is equal to C root of R S naught was the equation for uniform flow. So for non-uniform flow it is going to be V is equal to C root of R S F. So for gradually varied flow, V is equal to C root of R S F. If velocity is C root of R S F, discharge is area into C root of RSF. Discharge value is given to us. Area is 20 into 5. Chassis constant is 60. And square root of RSF. R is hydraulic mean depth, which from module 3 you would remember is area divided by wetted perimeter into SF. So 50 is equal to 100 into 60 into square root of area is 20 into 5, wetted perimeter is width plus twice the depth, so 20 plus 2 into 5 into SF, which from this equation you can see that SF is the only unknown it can be solved for, and I will get SF is equal to 0.0000208. So once I get the value of SF, I know all the remaining values. I can use the equation dy by dx is equal to S naught minus SF divided by 1 minus q squared divided by 2gy cubed. Small q squared is known to me, S naught is known to me, SF has been computed by me, depth of flow is given, and so we can find out the value of dy by dx by simply substituting in this equation. So I've substituted the values in the given equation and ended up as dy by dx is equal to 2.304 into 10 raised to minus 4. This is how you solve problems in gradually varied flow using the dynamic equation. It's a very simple equation. I've just given you 3 variations for it because you can use either form. All of them lead to the same thing, which is S0 minus SF divided by 1 minus FR squared. But if you have these formulae ready-made in your hand, you would be easily able to apply it according to the data that is given to you. Now, before concluding this presentation, let me talk about backwater curve and drawdown curve. Now, we know the equation dy by dx is equal to S0 minus SF divided by 1 minus FR squared. Now, if dy by dx is positive, it's a positive value, it means the depth of flow increases along the direction of flow. So, when depth of flow increases with direction of flow, it is known as backwater curve. Now, when dy by dx becomes negative, it means that the depth of flow is decreasing along the direction of flow, and such water surface curve is called drawdown curve. So I'll explain backwater curve and drawdown curve using a small figure. So this is the direction of flow. If the water surface had gone like this, that is, you can see the water surface, the water depth is increasing along the direction of flow, then this curve is known as the backwater curve. And if the water surface has gone down like this along the direction of flow, then it is known as a drawdown curve. So this is a backwater curve and this is a drawdown curve. Here you can see if the water surface had actually taken this path, it would have meant that the depth of flow is decreasing along the flow direction, and it's a drawdown curve. If the water surface depth was increasing along the flow direction, it would have been a backwater curve. So these are the basics of gradually varied flow. The more advanced topics I will be discussing soon for self-assessment. If you have gone through the video lecture, if you have understood what has been taught to you, these problems would be simple. You can try solving them so that you will be able to assess yourself whether you have understood the topic and whether you're comfortable with this given topic. So thank you for listening, and I hope you have understood.